5.2, today's lesson is going to focus on one concept today, and that is simulations. So what we are going to basically do today is perform simulations on some sort of probability event, something that's going to be described in a problem, and we're going to actually run a simulation of it to estimate, what the probability will be. Or we might run a simulation to test whether or not what happened in some sort of probability event is reasonable or not. Okay? So when we do a simulation, we actually try to follow this kind of 4-step process that we've been doing in the past, like when we started doing normal probability problems. We're going to state what we're trying to find or simulate. Okay? We're going to actually write out the plan. Then we're actually going to do it, which will more than likely involve our random number table in some way, shape, or form. Okay? And then we'll actually conclude our results. We'll actually state what did we actually find in our results. So basically today, we're going to show you a couple simulations. Okay? So on this first example, it says you are at a local school raffle and decided to buy a bunch of raffle tickets. Okay? You're actually that person that just buys tons of them hoping to win all the prizes. Okay? You bought so many that your chances of winning any one prize is 0.45. There are 5 big prizes possible to win. Okay? Design and carry out a simulation to see how many of the 5 big prizes you actually win. Repeat the simulation 4 times to see how often you win 3 or more of the prizes. So, to do this problem, the first thing we want to do is state what we're trying to find. Well, we're actually trying to see how often do we win 3 or more prizes at this local school raffle. So I'm trying to figure out that probability. I want to know how often am I winning 3 or more prizes. I've got a 45% chance of winning 1. So what's the probability, though, of the 5 big prizes that I'm going to go home with at least 3 of them? This up a little bit. So, what's going to be our plan? Well, what I need to do is I need to set up a simulation for each and every drawing of a prize. So what's the chance of me winning a prize? 0.45. Okay? So if I'm thinking about 0.45, if I think of 0.45 as a fraction, what is that? 0.45 as a fraction, I could write it as what? 45 out of 100. So if I'm going to do a simulation and use random numbers, okay, I could use 3-digit numbers, or actually I could use 2-digit numbers, 00 or 01 to 99, or really 00 to represent 100, where I'm going to let some of those numbers represent winning the prize, and some of those numbers not winning the prize. Okay? So that's going to be the start of my plan. I'm going to use the random number table to simulate winning a big prize. I'm going to assign 2-digit numbers where 01 to 45 represents winning, and 46 to 00 represents not winning the big prize. Are you okay with how I decided my number assignment? So if this probability wasn't 45 but was 75, then I'd do 01 to 75 and 76 to 00. So what's nice about my probability is, since it's only, a 2-digit, or you could say 2-digit probability, I could use 2-digit numbers. If it was like 70%, it would be even nicer, because then I could use 1 digit, and then I could go, 1 to 7, 8 to 0. Basically meaning 8 to 10. So, how many numbers do I actually want to select here? How many prizes am I looking at? 5 big prizes. So I'm going to select 5 numbers, but I want to see how many of them, of those 5, are in this particular range. So I'm going to select sets of 5 2-digit numbers and count how many of the 5 represent winning a big prize. That would simulate doing like one simulation, or calculating out whether or not I actually got 3 or more prizes. But how many times do I want to repeat this process? Okay, so I want to repeat it 4 times. So I'll just say repeat the simulation 4 times. Then determine how many of the 4 simulations has one winning 3 or more prizes. Because that will be our probability. So if it happens 0 times out of the 4, my probability would be 0. Happens 1 time where I win 3 or more, 1 out of 4. 2 out of 4, 3 out of 4, or if it happened all 4 times, my probability would be 100%. So just like when we were picking random samples, you can actually simulate all sorts of experiments that involve a probability. So now I actually have to do the simulation. So since I see a few of you still writing, I'll wait a second here. Bless you.
So when you use table D, how are you going to know which line to use?
Well, great question. Here it doesn't specify, does it? When you did some of the homework problems using the random number table, did it specify where to start? A lot of times it did. How about on your exam? Did I give you a random number, chunk of a random number table? Yeah. And I would just look at, all right, how did you assign them? How did you choose them? Okay, did you include all the information needed, okay, in your explanation? So here the problem doesn't. So I'm going to actually just throw up a chunk of the random number table. Okay?
So like normally, will you give us the table again?
Yes.
Okay.
Yep, on a test, if I were to give you, just like on your last test, there was that chunk of the random number table. So like here, what I did was I just wrote, whoa, sorry about that, I hate that when it does that. When I do that, I wrote down 4 lines of the random number table. I started at line 147, 148, 149, and 150. I used the last 4 lines of the random number table. However, could you start it at line 101? Absolutely. And notice how I just wrote just the first 10 numbers because I was collecting sets of 5 2-digit numbers. Now, could I have just used line 147 and use the entire line and then part of line 148? Absolutely. So now, what I'm going to do here is actually demonstrate and show how many prizes I actually win. So if the number is between 0, 1, and 45, I win. If it's 46 to 00, I don't win the prize. So for the first trial, 54, is that a win or a loss? I didn't win, so I lost. 97, loss. 38, I won. 62, loss. 78, loss. So for this trial, I won 1 win, and I have 4 losses. So I only won 1 out of 5 prizes. I'll put this instead of saying 1 W, 4 losses. So the first time I simulated it, I only won 1 big prize. Dang it. I want to win more than that. So I do it again. Let's do the next one. 00, is that a win? It's actually a loss, isn't it? 69, loss. 40, hey! 59, 77. Oh man, I'm not doing so hot here. Only 1 win and 4 losses again. So 1 out of 5 prizes. So I do it again. Thank goodness I only asked you to do it 4 times instead of 400. That'd be neat. So let's see, 71, nope. 54, nope. 60, nope. Man, 52, nope. 33, oh, at least I won that one. So that's 1 win. Again, 4 losses. That seems to be the theme here. 1 out of 5. Let's do the last line. 07. Hey! That's a good start. 51. 18. Yeah! 89. 15. Woohoo! Guess what? Did I just win 3 or more prizes? What? Yeah. I love statistics. I love probability even more. This is like games. So in this case, I actually won 3 out of 5 prizes. So when I'm looking at my final solution, says I need to calculate out my probability. This is the only one of the 4 that actually meets what I'm looking for. So what's my probability? Kind of almost gave it away. How many out of 4? Really? 1. Thank you. So the probability that you win 3 or more prizes in this simulation is 1 out of 4. Now, could you get a totally different answer than mine? And have a different conclusion? Absolutely. We know that there's variability. Alright? Even if I told you to start at the same place, if you continued on, going straight across versus going down, we could get different answers. So this is what you would have in a simulation. So, this one's nice because you're given the exact probability of an outcome. So all the random numbers you're using, okay, on the table is either like a yes or no. I don't have to ignore anything and note that. However, in the second example, a little different. Give you a second here, you can see a couple pencils still going. So I know, look at the second example on the next page. It's just one problem. I give you the entire page. Are you scared? A little bit? That's not too bad. Go figure, scary problem on Halloween. You know. That's why they paid me the big dollars. Including decimal points? All right, let's go to the next page and look at our last example here. Oh, I like this problem. It says, at a local high school, 95 students have permission to park on campus. So probably it's a much smaller school than here at Hopkins High School. How many parking spots do we have out there? Any idea? 400, 500? Do they number them from 1 to... Do they start with 1 or do they start with 100? Because I often wonder about that. Do they actually put a 001 up there? Or do they put a 1? Do they start with 100? Just so that the digits are all 3 digits? Ooh, let's check at 235. Sounds good. Yeah. So anyway, getting back to this. It says each month the student council holds a golden ticket parking lottery. Nice. At a school assembly. Sorry, didn't finish the sentence. The 2 lucky winners are given reserved parking spots next to the school's main entrance. It's kind of a good idea. Okay. Do we do that here? Well, oh, do they raffle them off at some like fundraiser? Okay. Good to know. Last month, the winning tickets were drawn by a student council member from the AP Stats class. When both golden tickets went to members of that same class, some people thought the lottery had been rigged. Okay. There are 28 students in the AP Stats class, all of whom are eligible to park on campus. Okay. Design and carry out a simulation to decide whether it's plausible that the lottery was carried out fairly. So how often would it actually occur that you would actually get 2 students from this class? That's what we want to see. All right, so, okay, first thing we want to do is figure out what's the probability that a fair lottery would actually result in 2 winners being from this AP Stats class. And based on this answer, was the lottery rigged? So we're going to simulate it. We're going to simulate it many times. Is 1,000 times too many? Yeah, probably. Is 100 times too many? 50 times too many?
5 times.
Alright, I'll go 30 times. 5 probably not going to be enough.
15.
Yeah, let's do it.
Let's do 10.
I have it set up, we're doing 30. But you'd want to see it many times. Because, boy, you know, if it happened 1 time in 10, would you consider it rigged? How about 1 time in 20? Maybe. 1 time in 30? Okay. 1 time in 40? 1 time in 50. So you can see doing more and more simulations might be helpful here. Alright, so now I got to do the random assignment. How many students are in this AP Stats class? 28. So I'm going to assign 2-digit numbers to those 28 students. 0, 1 to 28. How many students can park? 95. So student 29 through 95 are students that can park but aren't in the AP Stats class. But I still have other digits to deal with. 96 to 00, what should I do with those? Okay, I should just plainly ignore them. So I need to note that, so when it comes up, I need to know what I need to do with it. Cross it out or ignore it. Okay? So, start with the random assignment. So I'm going to use the random number table to simulate choosing the gold ticket winners. I'm going to assign a 2-digit number to the students where 01 to 28 represents a student from the AP class. 29 to 95 are not from the AP Stats class. 96 to 00 we ignore. What's that?
What are you tired? Well, now because she put it on my elbow.
So once we have the digits assigned to who's in the class, who's not in the class, which ones we don't want to even work with, we have to decide how are we doing the simulation. How many tickets are we drawing out? 2. So we're going to select 2 two-digit numbers at a time. So we're going to actually look at 2 sets of 2-digit numbers. We're going to know, are they in the class or are they not in the class? If they're in the class, or if I get both that are in the class, it's a success. If they're not in the class, or if 1 or 2 of them, then it doesn't happen. Okay? So we're going to select sets of 2-digit numbers and determine how many of the 2 are in the AP Stats class. We'll repeat this process 30 times and count how many of the 30 have 2 AP Stats students in them. And we'll see, is it reasonable? Does it happen quite often, or does it never happen or rarely happen? Move this up, and then I'm going to pull down the random numbers. So this is how many lines I actually have to use. I started at line 101. You can start anywhere. And I actually continue. This is all of line 101. This is all of line 102. And all of line 103. And all of line 104. Move the numbers up a little bit so it's a little easier in the back to see it. I'll give you a little bit of time. I know it's a lot of numbers to write. about 30 more seconds. Hopefully that'll be enough. We'll start doing the actual simulation. Alright, so we have to select sets of 2-digit numbers. Make sure that I'm on still on purple, good. So, here's my first set of 2-digit numbers, 19 and 22. Are both those students in the class? Are they between 1 and 28? Yeah, so this first set is a yes. Wow, just like that, first try, got it. Well, let's see if that continues to hold. Second set. The numbers are, is that 39 and 50? Because I circled them. Both of them are not, so that would be a no. I gotta be careful about circling them. So 34 and 5. 5 is, but is 34? So that's a no. 75 and 62. That would be a no. 87 and 13. That would be a no, because 87 is not what 13 is. 96. What do I do with 96? Ignore it. So 40 and 91. That would be a no. I feel like did I miss a number?
Yeah, you missed one.
I missed one, didn't I? 4, 96. But 96 I don't count. Do I? Because, no, I'm okay. Alright, the next set. 25 and 31. No. Because is 31 a possibility? No. 42 and 54. That'd be a no. 48 and 28. 28 is, but 48? No. 53 and 73 would be a no. Wow, we have one yes right away, and I haven't gotten one yet since then. 67 and 64. No. 71 and 50. No. Ooh, here's 99. Going to ignore that number. 40 and ignore 00 and 19. That would be a no. 40 is a no. 27. Would we select 27 again? Note about repeats. I should ignore 27 because that's the same student. And 54, or sorry, not 54, sorry, 75. That'd be a no. 44 and 26. That would be a no. Wow. 48 and 82. No. 42 and 53. No. 62 and 90. No. Wow, how many have I done so far? Well, have we done 30 yet? 2, 4, 6, 8, 10, 12, 14, 16, 17, 18. So right now we have one no, or one yes, 17 no. I'll switch colors so that I know that I only need to do 12 more. Alright, so 45 and 46, no. 77 and 17, no. 9 and 77, no. 55 and 80, no. Ignore 00, but 95 I can take, so that would be a no. 86 and 23, no. 94 and 85, no. 82 and 22, no. 69, ignore 00 and 56, That would be a no. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I only got to do 3 more. Thank goodness. 52 and 71. No. 13. Oh, and 88. No. 89 and 93. No. 7 and 46. No. 2, 4, 6, 8, 10, 12. Well, I actually did 13, so this one I could ignore. That was one too many. So I had another 12 no. So how many times did it actually happen? It happened 1 time out of 30. So, based on our simulation, both winners came from the AP Stats class only 1 time in 30 tries. Okay. 1 time out of 30. What is that as a probability or as a decimal? 1 divided by 30 is like what, 0.03? 0.03 something? Yeah. Like the 03 is repeating. Yeah.
No, like the 3s.
Just the 3 afterwards?
Yeah. Lots of 3s.
So, based on this, is it possible? Yeah, we had it happen. Is it probable? Right? Probably not. Okay? So it's possible that the lottery was conducted fairly, but our results are suggesting that it was highly unlikely. 1 in 30, not happening very likely. So most likely it was rigged. Not 100%, because obviously it actually happened, but wow, this is pretty unlikely. Is it beyond a reasonable doubt? Is 1 out of 30 reasonable enough for you? Okay, you might want to have more. Okay, and that's where statistics can lead into our judicial system. What do we consider reasonable doubt? What do people consider? 1 in 30, 1 in 100, 1 in 1,000, 1 in a million? Okay. All right. That is it for your notes today.